Good morning, everybody. So today we have the pleasure of to have a seminar by Miguel Romao. Just a short presentation of Miguel. Miguel got his PhD in string phenomenology at the University of Southampton, and then he did there a postdoc. Afterwards, he moved to Talent Ticker, an AI-focused startup in Cardiff, where he was the principal machine learning engineer and data scientist. After some time, he moved to Leap. He has been in Leap since May 2019, working on the Big HEP data project, where he has been developing machine learning analysis for high energy physics. And recently, he transitioned to the Strong 2020 project, where he's been using similar tools to study jet quenching phenomena. So today, Miguel is going to talk to us on how to use deep learning methods to search for rare events and beyond the standard model physics. Miguel.
Thank you, Ruben, for the nice introduction. So I'm going to talk about some work that we have done and some ongoing work using deep learning to search and study rare events, rare phenomena at colliders. So this is more or less the outline. I'm going to give a very quick introduction to machine learning and deep learning, because I think that it's still not, the knowledge in the community is not mature to the point that everyone knows exactly what I'm talking about. So it might be worthwhile for some people. And I'm going to talk about some work that we've done on using deep learning for try to develop more generic searches of new physics at the LHC. And then I'm going to talk about, in section 3, something that I'm working also with a lot of people in the audience and at LIP on studying of jet quenching phenomena through the Quark Gluon Plasma. Okay, then I'm obviously concluding at some point. So a very quick introduction to machine learning. So machine learning can be seen as a subfield of AI that concerns how a machine can learn to perform tasks. You can think about it as being self-taught code in the sense that it's a new paradigm of how you program a code. So instead of explicitly write the rules on how a program deals with data, you write a program that will eventually learn how to deal with data. So in classical programming, the programmer inputs the rules into the code, and then it gets a program that encodes this decision function, how to process data to derive answers. In machine learning, what you have is a lot of data which already has some answers. And what you do is you develop an algorithm that then will develop the code that will be able to process future data, so new unseen data, to reproduce similar answers. Deep learning in itself is just a subclass of machine learning algorithms that train the so-called neural networks to perform those tasks. So there's a variety, there's a huge variety of different machine learning algorithms and classes, and deep learning is just a subset of it. So what is actually being done in deep learning? So neural networks, which have arguably a terrible name, but also in physics, we are not very good at naming things, so we should be give a leeway to computer scientists. But the idea is that you have this object, which are the neural networks, which is just basically a function of some input to a certain output. And this function is basically a composition of these so-called hidden layers, and each hidden layer, basically what it does, it is a linear unit of the outputs of the previous one, and then goes through a non-linear activation function, which can be the hyperbolic tan. It can also be a sigmoid, which is basically a function which is bound between 0 and 1, and etc. So in the end of the day, you have to think about the neural network as just being a mapping from the inputs to a certain output. Now that output will depend greatly on the task at hand. So if you want to classify between two classes, as we're going to see today, you basically have one output that outputs between 0 and 1, being the probability of belonging to the class 1. But you can also have multiple outputs. For example, if you want to tag boson jets from quark jets, from gluon jets, and etc. What the training in the end of the day is going to be adapting these weights, which are at these linear linear units, so this linear transformation. So these matrices W and these vectors B, called the weights and the biases, are learnable parameters, and they will be adapted iteratively in training using what's so-called stochastic gradient descent. So it's important to understand that these are basically differential blocks, and so they can learn tasks and functions through differentiable loss functions, as you're going to see a bit. What makes them very powerful is that they have a huge representational power and feature abstraction. What I mean by this is that your variables in the beginning can be mostly unstructured and have almost no pretreatment or no human biases. And the neural network itself is going to learn progressively higher levels of abstraction as the layers go deeper and deeper to derive the relevant nonlinear and complex relations in the data. So this is very good and is the reason why it can provide huge discriminative power, but also can be applied to other different applications. Very importantly is also to say that the input data can take many formats, and this is very unique and different from a lot of the other machine learning algorithms, and namely the classic shallow ones. For example, you can feed images, sounds, text, and etc. So this has led to a wealth of applications. And nowadays, almost everything that is being processed, is processing huge amounts of data, is actually machine learning with a strong base in deep learning architectures in the back. I'm talking about Google Translate, I'm talking about YouTube, filter systems, recommendation systems in Netflix, and etc. So the loss function is important because the loss function is going to measure how a model is performing as a task at hand. So for example, if you want to use the neural network to approximate a function, so that would be a regression problem, just like a linear regression, but in this case, the neural network would be able to approximate, in principle, any non-linear, well, continuously, which is one function, but that's a small detail. And what you would use would then be the mean squared error, which is exactly the same loss function that you use to do a linear regression, for example. So, and then what you're going to do to train it is you're going to take the derivative of this loss function in terms of the weights of the neural network, and it iteratively in mini batches, which can be parallelized, you will then make the neural network learn the function better and better each time. If you want to do something like a classification problem, when you have exclusive classes, you use what's called the cross entropy, and so this will make the neural network to try to maximize the probability being 1 to the right class, and at the same time trying to get the probability to 0 on the wrong classes. So in HAP, we have huge amounts of data, and we are probably the only non-industrial set that can be comparable to the big five, so the Microsoft, Google, Amazon, Apple, and Facebook. And our data also comes in many shapes. In this talk, we're going to focus on two types of data mostly. So the ones which are used for or at searches for new physics at colliders, which are high-level physical observables from reconstructed objects. I'm talking about leptons with explicit flavor and jets, both small r and large r, and all of their observables like FFIs, PTs, masses, and etc. And then we're going to talk a little bit in the end about low-level detector information, where you basically take the calorimeter of an experiment as a camera that takes a snapshot of an event. And so the calorimeter cells are pixels of a picture, and then we try to do physics on top of those. So starting with deep learning to provide us better generic searches for new physics. So when you're looking for new physics at LHC or any type of collider, what you normally do is you choose a BSM signal that you're looking for. It can be supersymmetry, can be something else. Then you study your model to try to understand what would be the favorable kinematic and final state topologies where you think you would be able to find a signal at the collider or experiment at hand. You collect the data in such regimes and you apply the cards, and then you perform statistical tests on the data, on the hypothesis that that signal is in the data. And then eventually you'll profit or someone else gets a Nobel Prize for you, but that's the end of the day, that's the general idea. Operationally, what you normally have, you have these high-level variables from reconstructed objects. For example, on the right-hand side, you can see an example of the invariant mass of 4 leptons, reconstructed 4 leptons. Then you try to isolate a signal as much possible from the background. So the rule of thumb is to look for the signal region that maximizes the so-called significance, so that you try to get as much of the signal as possible, trying to get rid as much of the background as possible. And then you perform statistical tests on the sample that you have, on the variables that you have. And for example, you can derive upper limits on the expectation cross sections using the CLS method, which is here. So here I'm exemplifying the Higgs, both here in this reconstructed for lepton channel, but also here to show the so-called Brazilian plots that you get from the CLS methods, where here you can see that you cannot ignore the existence of Higgs in that region anymore. So how machine learning can help with this? So you can train a machine learning classifier to differentiate between background and signal. And so this will help you in principle to get rid of a lot of backgrounds. You can imagine this as being, in a certain sense, like a non-linear elaborate cut. So for example, here on the right-hand side, we have an example of boosted decision tree, trying to separate Higgs gamma-gamma events from other similar background events in order to try to maximize the significance of the Higgs gamma-gamma signal. So this was used in the Higgs discovery. So it's already an example on how machine learning is already driving discovery. And then what you can do is either you use this, so this would be how likely it is to be Higgs and how likely it is to be background. So you could use this score either to choose like an operating point and cut off to maximize the significance in your other variables, or you can immediately do, for example, limits on this variable. So you basically turn a multivariate problem into almost a univariate problem to perform the limits. So what have we done? We came across the question while we were playing a bit. So this was a bit on our earlier ideas when I joined the Big Data Hub project, which is if I train a neural network to differentiate between background to a specific signal, how will it perform if the signal in the sample is different from the one it was trained on? And how would this impact the derived upper limits on the physics on those signals? With that in mind, so we prepared 3 classes of signals, one which is an FCNC associated with top production, where we have an effective Z coupling, which is altered to allow for a flavor changing neutral currents. Then we have 2 classes of signals with vector-like quarks, which are vector-like T-type quarks, one which is produced through the standard model gluon, whereas the other one is produced through a BSM heavy gluon, so something that could come from composite Higgs models or similar models. So the best analogy that you can get with this is you train the neural network to differentiate the background, which would be like the jungle, from a specific animal that you're looking for. Like in the right-hand side, you'll be training it to try to find monkeys in a jungle. But what happens if the jungle does not have monkeys, but has pink panthers or some other type of animal? And how would the neural network tell you, well, wait a second, that is not jungle, or it is jungle? So what have we done? So we prepared a standard model cocktail sample. We produce in MudGraph with the usual pipeline of PTA and Delphs with a CMS default card. So we prepared 8 million Z plus jets, and then some TT bars and some boson samples. So we target processes with the leptonic final states, with at least 1 bit tag, and we did a HT cut of 500 GeV. I should have put the units there, I'm sorry about that. Also, to guarantee the statistics at the total distribution, we applied event filters. So we produced a sample for lower PT, for mid PT, and high PT, just to be sure that we had statistics that would cover the tails of the distributions. And then in the end, what we have is that an event is completely represented by these reconstructed variables of reconstructed objects. So we have the information of the 5 leading and 5 leading small r and 5 leading large R jets. So we have 10 jets here. And we have 4 leptons, 2 electrons and 2 muons. And then we have global event variables like the multiplicities of electrons, multiplicities of leptons, multiplicities of jets, and then also the missing ET and missing phi. So the signals are, we prepared 7 different samples covering 3 classes. So as you can see, our idea initially was try to understand, for example, how would the sensitivity change as you change the mass or would say a parameter of the BSM theory, but also its kinematic regime, because if your vector-like quark is being produced by a heavy gluon, not gluon, so we would put a 3TeV, this is going to be a highly boosted object, whereas here this production will be similar to the standard model. And in the edge case, we prepare this FCNC, which has final state and kinematics, which are very similar to the standard model. So we would like to know how the neural networks trained on all of these different signals would then perform, trying to discriminate when the sample has one of the other signals. So our methodology was to train a DNN classifier, so a deep neural network classifier to differentiate between signal and train for each of the signals. We kept the background constant, so it's the same background, so we are in the same kinematic regime. And then we used each one of these neural networks on different signal background combinations. So we basically used all of the pairings between those signals and training and test. So and then we assess how the discrimination will deteriorate when the signal present in the sample is different, and how this affects the limits, the upper limits on the expected cross section. So these are some of the results that we got. So you can see that, for example, here, I'm pretty sure that these are both for the same model. So this is for a model trained on the vector-like T heavy core, which was produced in the standard model, so without a heavy gluon. And you can see, for example, that for all the signals which have vector-like quarks in the final state, they perform very well if you just look at the ROC curves. The FCNC does not show here because notice that this is actually quite zoomed in to the top right corner of the ROC curve. But the FCNC still gets an area under the curve which is bigger than 0.5, so there's still discriminative power there. Here you can see again zoomed in on so these are the outputs of the neural network for different signals, and here zoomed in for the really high probability. So the ones that neural network thinks they are very likely to be signal. And so you can see again that the VLQs are being quite well differentiated, but still there's an accumulation of the FCNC here at the right hand of the spectrum. So here, for example, would be how the FCNC can be found when using models trained on all of the others. So unsurprisingly, the model that was trained on the FCNC is the one that performs the best. More surprisingly is that the models were trained on vector-like quarks can still provide a fairly good discriminative power. And this is interesting because the signals with vector-like quarks are very, very different from the FCNC, both in kinematics and final states. So then we derive the upper limits. On the left-hand side, we have the absolute value, but they are not that meaningful. What is meaningful is to try to understand how the limits change once you go from the dedicated neural network, which are the ones that are trained on a certain signal, and then we derive the limits on the same signal. So that would be the diagonal terms. So we then normalize this heat map to the diagonal terms. And so we can see, for example, how it deteriorates. So for an FCNC signal, the neural network that was trained on the FCNC obviously has one because it's normalized to that value, but then we lose around an order of magnitude sensitivity on discovering FCNC if the neural network could have been trained on other signals. So you can read this like, then you can read the remaining of this heat map the same way. For example, you can see very interestingly is that the neural network training on FCNC provides still a sensitivity which does not degrade, only degrades up to an order of magnitude on vector-like quarks. And the vector-like quark signal all seem to be quite transferable. So you have to take in consideration that there are statistical errors here, which are not shown in this heat map, but in the paper we put a table with all the errors. So these are compatible within those errors. So it seems that as long as you have a vector-like quark in the final state, it's basically irrelevant both in the mass point that you are calculating it, but also if it was produced in a highly boosted regime through a heavy gluon or not. So this was a bit of a surprising result. But then obviously the next question is, can we train something that just learns about the standard model background and ignores or doesn't know the specific BSM signal, and how would then behave when deriving limits on any BSM signal? So this is what we set out to do. So this is not only our idea, as you can imagine. So unsupervised methods are starting to gain really a lot of traction and interest in HAP community, exactly because they offer this idea that they can provide generic searches. In specific, we'll be looking at what they are called anomaly detection algorithms in machine learning, which are algorithms which are learned learn about what's only one class, in this case background, and try to assign a so-called anomaly score to a new instance on how likely it is to be an anomaly, considering that it learned only on background. So there's already been some work on this, and I also advise you that GitHub from the CERN's International Machine Learning Workgroup, which they keep a curated and up-to-date review on all the machine learning papers in HAP, and there are other references there. So what we did, we kept the signals the same and the background the same. So basically we reused the samples. But then what we did was we used 4 different anomaly detection algorithms. So in the community, there's already been some work with autoencoders and variations, namely variation autoencoders. But what we then set up to do was to present 3 others which haven't been used yet in the community, and for the first time actually compare how different anomaly detection algorithms behave, comparing between them. So the first one is the autoencoder. So the autoencoder is a neural network that learns how to encode the input into a smaller dimensional space. So the idea is that this intermediate layer has a dimension which is a lot smaller than the input space. And so it will have to learn how to encode the data into that space. And then with that information, re-decode it or decode it, reconstructed back to the original shape. And so how well this neural network reconstructs it shows you how well it's learning how to encode into this, so projecting to a smaller dimensional space. What we'll then use is that in principle, the neural network, so in principle, the autoencoder will learn how to reconstruct the easier or the most common events. And so the events which are more difficult, rarer, will then be, will have a higher reconstruction error, and then there will be a target as being an anomaly and maybe candidates for BSM signals. So the learning target is this reconstruction error that we want to minimize during training. And so the idea is that the BSM events of BSM signals will have, on average, statistically speaking, higher reconstruction errors. Another neural network that we propose is the so-called Dpass VDD. SVDD stands for Support Vector Data Discrimination. So again, a mouthful. But here the idea is that you try to project the data into a certain space. So remember that the neural network at the end of the day is just a map, just a function from the input to a certain output. But then, so this will provide an embedding in this space called Z. So here we call Z. And then the idea is that in the beginning, before even training, the neural network, so the weights are initialized randomly, the neural network will project these events into this abstract latent space, doesn't matter what it means. And in this space, you can actually compute the center of mass of this distribution. What you can do next then is try to collapse the points into this center of mass. And again, so basically you're going to try to minimize the distance of the points to the center of mass in this embedding space. And then, so the idea is that the bulk of the distribution, so where the most of the weight of the distribution is, will be easier to collapse because the center of mass is already close to it. And then the most outlying points will be, so the ones which will be further away from the center of mass will then be considered anomaly. So the distance to the center C is called, will be our measurement of an anomaly. So this will be how you derive an anomaly score with this network. Then we use 2 shallow algorithms. One of them is called the isolation forest. So in the isolation forest, what you do is that you randomly partition the data with random cuts. So you just pick up the features, a subsample of the points. You just pick up the features and you randomly partition those with random cuts. And then the idea is the more cuts you have to go through, coming from, for example, infinity to the last partition, the more cuts you go through, the more difficult it will be to isolate that point, which means the more common it is, that point. Whereas a point which is very outside, you will not cross these many cuts, and this is going to be most likely an anomaly. So the idea is you can drive an anomaly score by how many, so the anomaly score will be inverse to how many of these cuts you have to traverse in order to get to that point. So this is a way of doing it. So it's actually a very good one. It's a very interesting idea. A more obvious idea is just to use histograms. So we use this called the histogram-based outlying system. And basically what you do is that you compute the histograms for all your variables. And then once a new instance comes, if that instance consistently follows on shallow beams, it means that it's more unlikely than if it follows on tall beams. So basically the sum of the heights of the beams where an instance falls on is inversely correlated to how outlying it is. So we can use that. So basically your anomaly score is going to be associated with the heights of the beams. So you use the logs because these are going to be between 0 and 1. So the shallower it will be, the higher it will be the score of being an anomaly. So it's a very, very easy to implement. It provides yet another comparison. So the main point here is that you only use standard model events to train these 4 algorithms. You do not use any BSM signal. You do not use anything besides the standard model samples. And now what we want to know is how different are these algorithms behaving, how are they correlated, and what can we learn from their applications in such as for generic new physics. So first of all, and before continuing, we found something that was quite interesting. So when you're using high-level reconstructed variables, you're going to have a lot of missing values, right? Because not every event is going to have 3 or 4 leptons. Not every event is going to have 2 fat jets, and etc. So there are going to be a lot of missing values. This will lead to accumulations of densities in the input distributions around the missing values, which tend to be zeros and stuff like that. And neural networks do not like discontinuous inputs. So this is a problem that that's more or less known in the community, and this can hinder performance. So we then prepared a second set of features which attempts to mitigate this a bit. So for example, we demanded a fat jet and dropped all the remaining information of all the fat jets. And instead of keeping two electrons and 2 muons, we basically just kept 2 leptons and discarded the rest, regardless of their flavor. We do not completely mitigate this in the sense that we still kept subleading jets, which also have this accumulation. So this was a bit of an intermediate step, and we actually want to reserve future work to explore this issue further. So in order to understand this, for example, here is the autoencoder trying to reconstruct these 2 different variables. And you can see on the left, when we use the full features, this accumulation in 0, and you can see that the distribution of the reconstructed variable is not really on top of the actual variable. Whereas once you use the sanitized features, what we call sanitized features, so by requiring at least 1 fat jet, you don't have this accumulation anymore. And by using 2 leptons and only 2 reconstructed leptons, because we are in the dileptonic regime, there will always be 2 leptons. You also don't have this issue that you would have when keeping the flavor explicit. And you can see that the reconstructed events follow basically the same distribution. Obviously, as you go further to the tail, it starts to get a little bit worse, but that's expected. So one very important part in machine learning is to use a validation step. So in this case, we use, so initially our samples were divided into 3 different splits: training, validation, and test. The limits were only derived on the test set, and the validation is this intermediate set that you use just to validate what you've done before going to derive the final results in the test set. You can see here in the validation set that the 4 algorithms are producing anomaly scores which are compatible between the training and the validation set, so there is no risk of being overfitting to the data that we fed it. It's also an important step. So, and how are these algorithms correlated? And Surprisingly, they're not. So we were not completely expecting this. So the both shallow algorithms are quite correlated with each other, and they still seem to have some correlation to the autoencoder. But once you compare the autoencoder to the Dpass VDD, so the two deep learning based algorithms, they are not correlated. And here on the right-hand side, so we derived, so these are the distributions for what we call the outlier. So basically we kept, for each of the 4 algorithms, we kept the 10% most outlying events, just to get the feeling of what the algorithms were capturing. And you can see here that the Dpass VDD is learning something that the others are not learning. So the other 3 are clearly focusing on the tails of the distribution, whereas the Dpass VDD is apparently looking for more nonlinear notions of outlyingness. So this was an interesting result that we found. So what happens when you feed it signals? So these are the same signals as before. And you can see that all of them have the capacity to find new signals, in the sense that you can see that the anomaly score for all of the signals are shifted to the right. So the distribution are shifted to the right, so you do not have the same distribution as the background. The exception being that for the FCNC, both the iForest, not both the iForest, the histogram based, but also the autoencoder, it seems that the FCNC follows much distribution which is much more likely to the standard model than, for example, in the Dpass VDD. So here we expect that Dpass VDD to be better at getting the FCNC signal, whereas the autoencoder seems to be better at isolating the vector-like quark signals, for example. So we then derive limits on this. I have no idea what this is. This is just an artifact. So what are we seeing here? So our baseline is obviously a supervised DNN. So what we're trying to find is how the performance degrades when you go to a completely unsupervised regime, so versus a supervised regime. And we're trying to compare also the full features to the sanitized features. So our baseline is the supervised classifiers for the full features. So you can see, I think it's important to immediately jump into the sanitized features, because you can see immediately when comparing supervised DNNs with full and sanitized features that using sanitized features improves the performance of the neural networks, just even in the supervised case. So our intuition that those accumulations of missing values are bad for the neural networks are being validated here. And then what happens with the anomaly detection is as such, as I said before, so the anomaly, the autoencoder seems to be quite good at getting the vector-like quarks, but not as much the FCNC, whereas the Dpass VDD seems to have a more similar performance across the board. So this was quite interesting. And in specific, it can get the FCNC quite well in comparison, for example, how it gets the VLQs and etc. We also see that the iForest does not perform as well, and even the histogram-based one is not as bad as the iForest, but cannot compete with the autoencoder and the Dpass VDD architectures. So what have we concluded so far is that neural networks provide a versatile solution for generic searches. So both the supervised classifiers, which was the first work that I presented, are very good at capturing signals from a different nature. So other BSM signals not used in the training. That's quite a surprising result. But also unsupervised architectures like autoencoder Dpass VDD can provide a very good sensitivity. You get a degradation of sensitivity of up around an order of magnitude, but still quite good. And what we also find is that there's still a lot of work to be done. So for example, this is very limited to the dileptonic case. We want to extend this to other kinematic and topological regimes that we are looking for. And we also want to diversify the BSM benchmarks, try to understand if what we found so far translates to other types of VSMs. Another thing that you might point out is that those limits are computed with the CLS method, which is when you compute the limits, you do have to use the true labels of being background and signal. So that's not a completely unsupervised statistical test. And that's true, and we're aware of that, and the community is also aware of that. So there is some work on how to perform statistical tests on, for example, on the output of the anomaly detection and to understand how can you do that part completely unsupervised. So we're also looking into that. So now I'm going to very quickly talk about another part of the work that we've been doing here at LIP using machine learning, which is using low-level data in rare phenomena studies. So deep learning, as I told you before, is very versatile. So in the previous section, I only talked to you about tabular data. So things come in CSVs or H5s or etc. But deep learning can take data in many different formats like images, text, and etc. Here we have an example of a fantastic Portuguese-Brazilian translation. And this is a neural network. It has been a neural network since 2014 that Google Translate used. And I don't know if you guys have noticed, but it has the quality of translations Google Translate has improved by leaps and bounds for the past 6-7 years. And it's exactly because they started using this type of architectures. So at LHC, before you reconstruct objects and their variables, all that you have are very low-level data from the detector, right? So for example, here on the right-hand side, we have an event, and what you have is calorimeter towers and track towers as well. So, and you can see that basically this can be taken as pictures, because basically what you have is a picture here, and each pixel, the density of the picture was just the amount of energy deposited in the calorimeter cell will just be the density of the pixel. And so you can use, for example, calorimeter towers and tracks in conjugation to do physics with low-level data. So this again is not completely is not a truly novel idea. So it has been already explored before. And what you use is these computer vision architectures from deep learning, so convolutional neural networks and etc., that can intake images to perform tasks such as classification and etc. So in 2015, there was this first work called Jet Images Deep Learning Edition, and so they used these ideas to discriminate between W bosons and QCD multi-jet processes. And then a year later, there's this deep learning in color. Basically, they used a more convoluted idea, but they used similar approaches to discriminate between Quark and Gluon initiated jets with quite good performance. So what are we doing? So we are studying the phenomenon of jet quenching. So in the presence of the Quark Gluon Plasma, the jet is created inside the medium, and the initial stages of its life, it will traverse the medium and it will interact with it. So this will change the history and the history of the jet, and this phenomena we call jet quenching. And it's still ill understood because it's in a non-perturbative regime of QCD, so it's very difficult to explain or to derive observables that explain some of the experimental results. So we are using these ideas to try to go directly into calorimeter images, because they might provide a way of learning a little bit through jet substructure. So because you can see that the calorimeter images of an event encodes information about jet substructure. So this is something that we are working. So by me, I mean Miguel, Liliana, Felipe and Nuno. And these are super work in progress results. So I'm just going to go through very quickly. So one of the things that I've been working on with this collaboration is using this computer vision architectures. I've been focusing on two. One is the convolutional neural networks, where you have a receptive field that goes around the picture. So because it goes around the picture, it can learn position invariant features. Whereas the other one, which have been locally connected neural networks, where each area of the picture has its own dedicated receptive field, it will learn position-dependent features. So I think I've shown these plots already in Jornadas, but here we go again. So here with the convolutional one, you can see exactly what I was saying. So the receptive field is a 3x3, it has a 3x3 field, so area. So in the beginning, very early on in the network, you can only learn relations which are around in the 3x3 area, but as you go deeper and deeper into the network, the effective area of each filter increases, and it's learning position invariant features. So that's why these patterns are repeating, is because it's translational invariant. At the last layer, just before the classification, it's already learning event-wide features. So here you can see Oh, by the way, in this case, the red is the leading jet and the green is the subleading jet. So in this sample, when we derived this image that we were using, events with up to 2 jets. And so you can see that at the end, it's learning features that already occupy the entirety of the image because they're learning global event features. For the locally connected one, you don't have such beautiful pictures, but namely in the beginning, because it's a bit of a mess what's trying to learn, but in the end, you can already see that it's trying to learn something which is also dependent or sensitive to the global aspects of the event itself. So it's been something I've been working on for a while, and it's a lot more difficult than initially we thought it was going to be, but that's normal, that's research. So that there is, so the computer vision architectures that I myself have been working on seem to be able to differentiate between quench and unquenched jets, so jets that have been, that interacted through with the Quark Gluon Plasma, those that haven't. But however, the discriminative power of the computer vision techniques is quite mild, so we don't have a striking performance, and that has been making it quite difficult to immediately relate to more mature jet observables, both substructure and global. So we are trying to work on understanding this better. However, we are also expanding the study to include our representation of jet, namely, a very important one is a sequence of coordinates in the Lund plane, because those tell a story on how the jet developed, and this is the work that Felipe has done. And those are providing a lot strong discriminative power, so that's already some physical insight in there, although not completely unsurprising. And we're also always trying to think about other architectures, because in the end of the day, the computer vision architecture might be failing because of the assumptions of the architecture itself and not the information in the data. So there's an interplay here between be sure that the data has the physical information and be sure that the machine learning algorithm has access to it or can make use of it. So just to wrap up very quickly. So I hope that I've convinced you that deep learning provides paradigm shifting possibilities to search for rare phenomena at colliders. In this talk, I talked about 2 main approaches that we have been working on. One is to try to derive deep learning tools that can help us with generic searches of new physics. So this would, in this case, deep learning is a tool for discovery. But we're also trying to use its versatility, deep learning's versatility in inputting data from different formats to try to learn about an already non-existing rare phenomenon, which is the case of jet quenching. And so in that sense, deep learning is a tool for learning physics. And that's it. Thank you.
Thank you very much, Miguel, for this very interesting seminar. Now we have some time for questions. Please raise your hand or just make the question. There's no questions?
It was all very clear.
No, I have one, don't worry. Okay, so one of the things in neural networks is you have this abstract space, and then you try to teach the network to separate, to classify different populations. But in particle physics, we often use, when we do simulations, we weight the simulations so that rare events can be so frequent as common events. And what this does is that at the end, you have one single event that has a huge weight. And I know that this is usually a problem for neural networks. So you need to do some oversampling or things like that. So I imagine that you're getting these problems in your...
So not really, in the sense that neural networks, so maybe it's not clear. Let me just, so when you produce samples, any loss function will suffice. So when you produce samples using Monte Carlo, you have an idea on, you have the information on how rare an event is because of the cross section. So you can produce billions and billions and billions of Monte Carlo events for that process. And then you can basically reweight the weights, the cross-section, into weights that will tell you what's the actual statistical shape of that distribution. And here, when you use those functions in neural networks, you can actually, so here is taking the average of the events, but what is actually here is that we are using the weight. So the learning takes into consideration the statistics of the data, the physical statistics of the data. So the events which are 100 times more likely in the standard model will contribute 100 times more to the loss function than the others.
Yes, it's true, but then you need to have sufficient. For instance, what I'm saying is that imagine that I take one of those points and I say that all the points have weight 1, and then one of the points I say that has weight 1000.
Mm-hmm.
So in this case, the network is going to get fixed on that point, because it's going to say, "Wow, it's one single point in one phase space. So I want to really grab that point, right?" So
yeah,
how do you avoid this kind of problems? That's my question.
Well, I wouldn't say that's much of a problem, in the sense that, for example, if you have one point that's 100, for example, in this case in specific, where the data is pseudo data generated, right?
Mm-hmm, mm-hmm.
So you have complete control of what you are feeding to the network. If you have one point that has 100 and all the other points have 1, that means that you basically have to generate more Monte Carlo examples of the 100, and then feed it to the network with the reweights and etc., so that the statistics of the variables are as true, as close to the physical distributions as possible. Now you can say that if you are feeding events that have like 4 or 5 orders of magnitude lower, it might be the case that in the end their contribution to the loss function might be absolute marginal. Mm-hmm. That is something that one could actually study to see if they even, because the thing is, so you are multiplying this by the cross section. So there's an by this loss function. So there's an interplay here, which is the overall weights that you put here, which has to do with the cross sections, which has to do with how likely that event actually is in real life. But in the beginning, those events will be the ones that will drive the loss function, exactly because they have the highest weights, right? Good. So the neural network will start by learning those because they have the highest weights. So it means that in principle, this is going to be going to 0 faster for those. So there's an interplay, which is once this is actually small enough, then the smaller weights might kick in and might bring those events, the rare events, to contribute, okay? Because if it's learning first about the most common events, it also means that the error will approach 0 quicker for the smaller events.
Okay.
So yeah, that's a bit what I was thinking, that this is just the average loss, right? And so if a weighting could be used here because you know, more, well, let's say higher PT events of some new signal might be much more valuable, because they'll be much easier to distinguish from the background, won't they? Well, yes, but in general, and that's a bit maybe an over generalization.
I think you're right, but it's going to be very case by case, application by application.
Yeah.
Right? So, for example, in this case, which I think it takes a very much of an intuition in the notion of a statistical, of the background being a statistical distribution, because here what you're trying to do is trying to bring all the points of the background to the same point, right? And you want to do is first you bring the bulk of it, so the vast majority of the standard model points, which are the most common ones. So those will collapse very quickly to this point. And then you're going to have the rarer ones, which have like smaller cross sections, but eventually it will learn to pull them in as well. But yes, you can always adapt the loss in order, you can always get weights the way that you want. In our case, we use cross sections to keep this notion of the statistical distribution of the background. But if you want to keep more, if you want to give bigger relevance to PT, you can also drive weights which take into account PT, right? You can the weights can be whatever you want.
Right, but you're right. It then becomes a case by case thing, isn't it?
On the application of what you're actually looking for, isn't it?
Yeah.
Okay. Any more questions to Miguel? If not, I would like to thank Miguel for this very clear seminar, and the slides will be available later on the Indico webpage as well as the recording of this seminar. And I would like to thank you all for being here today, and I wish you a good day. Bye.
Okay. Thank you, guys. Thank you, Ruben. Bye.
Bye.